talk will be given by Tianchi Li on combining formal and informal information. Tianchi.
Okay, so thank you for your introduction. Good afternoon, everyone. I'm Tianchi Li from Peking University. And today I'm going to present my work on how to combine formal and informal information in Bayesian program analysis via soft evidence. And this is a joint work with my advisor, Zhang. So let's begin with the motivation. While conventional program analysis have developed for decades, they rely on the formal semantics of a program to reason about its behavior. However, programs also contain a lot of informal information that this analysis typically ignore. This kind of information includes the names of variables and methods, and string constants, and even comments. It can provide valuable hints that developers intuitively use to understand the code. For instance, variables which have similar names are more likely to alias with each other, and a code fragment commented with to-do is more likely to be a true bug. So the central question is how to incorporate such information in a formal program analysis. And this is a non-trivial problem due to the three main challenges. First is soundness. Informal information provides no soundness guarantee. Such information is a hint, but not a fact. We cannot treat it as absolute truth. And second is usefulness. A vast amount of informal information is irrelevant to any specific analysis goal. We need a way to identify and leverage the useful signals. And third is automation. To make the approach practical, it must not require significant manual effort. We need a scalable and automated way to extract and integrate these hints. And then I will use a motivating example to walk through our approach and explain how it resolves the three main challenges. Here we have a simple Java program performing a points-to analysis. We have an animal interface with dolphin and dog implementations. And then a wrapper object's content field is first assigned a dolphin object and then overwritten with a dog. The variable dog1 then retrieves this content. And the data flow suggests that variable dog1 points to the dog object created at line 2. There are two tap-down casts in this program. One at R1, casting dog1 to a dog, which is a safe cast. And another is at R2, inside the describe method, casting the parameter to a dolphin, which is unsafe. And the instance analysis is flow insensitive, so it will think dog1 can point to the dolphin object created at line 1, and then identify R1 as an unsafe cast, which results in a false alarm. By applying the above Datalog rules, we get a derivation graph. And as I analyzed before, the analysis derives two unsafe downcasts. This results in a true alarm for the cast dolphin, but a false alarm for the cast dog. However, we notice that the analysis reports the false alarm because it thinks dog1 may point to the dolphin object created at line 1, which means that dog1 alias with the variable dolphin. And similarly, for the variable dog and animal. But for a human programmer, it is more likely that dog aliases with animal, but not dolphin, since a dog is an animal, but not a dolphin. That is, we can predict whether a pair of variables alias with each other by their names. Now, by corresponding informal information to specific program facts, we can leverage the useful information. And to handle the uncertain nature of this information, our approach is built on Bayesian program analysis. So what is a Bayesian program analysis? It is an analysis paradigm that calculates the probability of alarms by converting the analysis into a Bayesian network. And it can incorporate external information as evidence to update the probabilities. This framework first converts the derivation graph into a Bayesian network by attaching probabilities to the Datalog rules. Here, for deterministic rules, we attach a probability of 1. And for approximate rules, we assume they have a probability of 0.9. And in practice, the rule probabilities can be obtained by training. It then calculates the marginal probabilities of the alarms and gets an alarm ranking. Initially, without any informal hints, the two alarms have a same probability of 0.9, making them indistinguishable. The core idea is to then observe evidence derived from our informal information to update these initial probabilities. And this allows us to reevaluate the likelihood of each alarm and produce a posterior ranking. In the process of Bayesian program analysis, only the ranking, but not the alarms themselves, is updated, so it provides us soundness guarantee. And here comes the central question: how to incorporate the informal information as evidence? In previous Bayesian analysis works, a user is given by an alarm and inspects whether the alarm is true. The user feedback is then set as an evidence, which is either true or false, and we call this as a hard evidence. So one would probably ask, can we just take the previous approach and substitute the user feedback to our informal feedback? For example, we can use a neural network to predict whether the alias relation holds by their variable names, and incorporate them as a hard evidence. But our answer is no. The main difference is that a user feedback is with high confidence, but the alias relation predicted by the variable names is a noisy information. In other words, we cannot definitely say whether two variables alias with each other only by their names. However, using hard evidence will lose such noisy information. In fact, what we consider is something like more likely versus less likely, rather than a simple yes or no. And in order to solve this problem, I then introduce our key technical contribution, soft evidence. So now I will introduce how the soft evidence mechanism is adopted. First, we can assign a confidence value for each alias tuple given their variable names. And in our work, the confidence is get from a neural network, which I will talk about later. We can see that the confidence for alias animal dog is larger, meaning that it is more likely for dog to alias with animal. If we consider hard evidence, for example, we can set a threshold, say 0.5, and any value above it will be set to a positive hard evidence, and its posterior probability will be forced to 1. But how to set the threshold is tricky. In such case, both the two alias tuples will be set to a positive evidence, leading to no difference. So instead, we adopt a soft evidence mechanism. Rather than forcing a fact's probability to 1, soft evidence adjusts it by a Bayes factor k, which increases the odds of the fact being true. And for implementation, we encode a noisy sensor T prime to the soft evidence fact, and the soft evidence on T will be equivalent to the hard evidence on T prime. The confidence of the alias tuple is assigned to the conditional probability and then converted to the Bayes factor. The more confidence we believe the alias tuple holds, the larger the Bayes factor is, and the larger its posterior probability is. After applying this soft evidence, the Bayesian analysis updates the alarm probabilities, and now the true alarm comes first. And here I will discuss about how to calculate the confidence value for the alias tuple using a neural network. To predict the likelihood of an alias relation, for instance, between dolphin and dog1, we take the variable names as input. And then we use a pre-trained model, GraphCodeBERT, to generate the semantic embeddings for these names. These embeddings are then fed into a simple, fully connected network that outputs a probability for the alias relation. For any program fact and its related informal information, we can use a similar framework to predict its likelihood. With the neural network and the soft evidence mechanism together, we can now automatically extract the informal information. So let me summarize our complete approach next. We start with a program to be analyzed. The Bayesian program analysis framework constructs a Bayesian network and calculates an alarm ranking. In parallel, our trained neural network processes the informal information extracted from the code to generate soft evidence. This soft evidence is then used to refine the probabilities of the alarms, producing a posterior ranking. And the Bayesian program analysis and the neural network can be trained offline. So here comes our evaluation. And we instantiated Dancer on two analysis tasks, a pointer analysis for Java and a taint analysis for Android apps. We ran our experiments on 8 Java benchmarks and 8 Android apps. The informal information we considered was variable names for aliasing in the pointer analysis and string constants for identifying intercomponent communication in the taint analysis. Our neural network was trained on a set of small programs demonstrating their ability to generalize. And I will use a small example to explain the informal information used in Android taint analysis. And in Android apps, different components can communicate with each other by intents. If the action field of an intent matches the intent filter of another component, then the intent can communicate to it, and the tainted value can propagate to another intent by intercomponent communication. And in this code fragment, the action store is get from a config file, and a static analysis tool cannot get it directly. Here, we can get the action field of intent I1 and I2. We can use the string constant fvigit update to predict I2 is more likely to match with the intent filter. And this chart shows the inversion count of alarm ranking, a metric where lower is better for both Java and Android benchmarks. There are 3 bars for each benchmark. The first is baseline, which is the vanilla Bayesian analysis without evidence. Our approach in orange considers the soft evidence. And the rightmost one is the oracle method, where the ground truth label is served as a hard evidence. We can see that for most benchmarks, our approach is significantly better than the baseline, and even close to the oracle. Then this table shows our improvement on inversion count, mean rank, and median rank, 3 other metrics for the ranking. And the results show that our approach can significantly improve the quality of alarm ranking by taking soft evidence from informal information. We also tested the sensitivity of NISA to different training sets. We divided the 8 benchmarks into 4 groups, and each time we use 1 group for training and the other 3 for testing. We found that our approach is robust. The choice of training set does not dramatically affect the outcome, and performance is stable and generally improves when more training data is provided, which is a desirable property. In addition to the informal information, the soft evidence framework can also be used to integrate dynamic information from test runs. Specifically, we make an evidence for the program fact, which is being tested. If we observe it in a test run, then we set a hard evidence on it, which suggests that it must hold. Otherwise, we set a soft evidence on it. And the more test runs we have, the more confidence we believe it does not hold. We evaluate the dynamic information on interval analysis and the taint analysis for C program. We compare our approach with DynaBoost, another analysis tool that incorporates dynamic information, but it does not provide a systematical way to incorporate such information. The results show that our approach is comparable to the state-of-the-art tool DynaBoost, but more systematic than it. So in conclusion, we have proposed a new paradigm that systematically combines formal and informal information in program analysis. And our core contribution is the use of soft evidence to integrate hints from a neural network into a Bayesian analysis framework. And our work is the first to integrate soft evidence in Bayesian program analysis. We also incorporate information from test runs using the mechanism. Our evaluation on Java pointer analysis and Android taint analysis confirms that this approach significantly improves the quality of alarm ranking. And thank you for your attention. And the code is available on my GitHub page.
Thank you, Tianchi. Any questions?
That was very nice. In your evaluation for Java, you had an FTP benchmark. That was the last benchmark on the right.
Okay.
And well, what I want to ask about is that it looked like the result there was better than the ground truth or the method based on ground truth, and it looked very different from the other ones. Yeah, see,
yes.
See how top right corner, right? What's going on there?
So in our evaluation, the posterior ranking is somehow depends on how the evidence is set, and there may be some wrongly generalizable for the Bayesian network, and it is somehow depends on it somehow depends on how the Bayesian network inference converts. So it may be because of different reasons.
Okay. Okay. So is the soft evidence only limited to the variable name aliasing right now, or are you also leveraging any information in the comments?
Oh yes. So so I have so actually we propose a principle for the how to incorporate the informal information. So and for other kinds of informal information, the principle is the same. So for example, you can find some relations that are corresponded to the comments. Say that you and in some previous work, it's the someone has used comments, interrupt related comments to identify whether interrupt bug is found. So yeah, maybe the principle is the same.
Yeah. Let's thank the speaker again.